Okay, guys, today we are learning about algorithms. First, we'll start with the definition. What is an algorithm? An algorithm is a formally defined procedure for performing some calculations, which basically means that it provides us a blueprint to do some calculations, okay, which guides us through all the steps that are required to execute something, execute a calculation and get an output. Okay, it is considered to be an effective procedure for solving a problem in finite number of steps. An algorithm is considered an effective procedure, which means that it has to be efficient for solving a problem that we have at hand in finite number of steps. Now, this sentence contains three important properties of an algorithm, which we'll discuss later in detail. Now, the third point says algorithms are mainly used to achieve software reuse. Now, this software reuse means that algorithms are general purpose, right? We can implement an algorithm in any language we want. Some people program in C, some program in C++, some Java, some Python, right? But algorithms remain the same. Okay, algorithms can be implemented in every language. Okay, this is what we mean by software reuse. Now we'll move on to the next slide. Here is an example of an algorithm. The problem statement is find odd or even, and here these three steps are the algorithm basically. The first step is input the first number as a. A here is suppose an integer variable. Since we are taking a number, we'll take a as an integer variable. So the first step is input the first number as a. The second step is if a modulus 0, a modulus 2 is equals to 0. Now this is the condition to check whether or not the number a is perfectly divisible by 2. If the number is perfectly divisible by 2, then we will print even, which means if this condition is true, then we will print even. If this condition becomes false, we print odd, because if it is not perfectly divisible by 2, then the number will be odd. The third step is to end the algorithm or to end the program. Okay, this is the algorithm. These three steps are the algorithm. Now we'll talk about the properties of an algorithm. Input is basically the data we taken to calculate and get the resulted get the result. Output is basically the result we get after executing that calculation. Finiteness is actually a very important aspect of an algorithm. Finiteness means that algorithm we are considering, it will take a certain fixed amount of time, a finite amount of time, and a reasonable and finite amount of space to be executed. Okay. For example, if an algorithm takes a million years to execute, that is not an algorithm. Finiteness is one of the fundamental properties of an algorithm. Similar to that is definiteness. Definiteness actually means that every single step of that algorithm must be rigorously and unambiguously defined. Okay. For each specific case, we have to specify in detail what are the steps, what do we have to do in each step. That is called definiteness, being definite, right? Order of sequence is the order of the steps which we have to perform. For example, you cannot end a program before starting it. Okay, you have to follow a certain pattern, right? For example, first we have to declare the variable, then take the input, then perform the calculation, then print the output, then end the program. Okay, that is the order of sequence. Correctness basically means the expected output of that algorithm and the actual output of that algorithm must match, right? If that is happening, then the algorithm is said to be correct. Okay. The third slide is about time and space complexity of an algorithm. First, we learn to analyze an algorithm means determining the amount of resources such as time and storage needed to execute it. Okay, here it says to analyze an algorithm means to perceive and process an algorithm means determining the amount of resources. We take into consideration two resources: the time required to run that algorithm and the storage space required, which is basically the computer memory required to run that algorithm. That is called analyzing an algorithm. Now, efficiency or complexity of an algorithm. Efficiency or complexity is basically the same thing, right? How efficient that program is or how complex that algorithm is stated in terms of time complexity and space complexity. Now, time complexity and space complexity, we'll learn about definitions. Asymptomatic notation is used to define time complexity. Okay, asymptomatic notation means the method by which we denote the time complexity, right? We have two or three methods, and the very basic one is and the important one is big O notation. We'll learn about that in detail later. Right? Time complexity of an algorithm is basically the running time of the program as a function of the input size. Now, this is the important part as a function of the input size. Okay, it doesn't just depend on the time. Okay, it depends on the input size as well. Okay, for a certain input size, what is the running time of that program? That is called the time complexity of an algorithm. And similarly, for a certain input size, what is the space required to run that program or that algorithm? It is called the space complexity of that algorithm. Now we move to the next slide. Calculating time complexity. We learned how what time complexity is and what space complexity is. Now we learn how to calculate time complexity. Okay. First, the efficiency of an algorithm is expressed in terms of the number of elements that has to be processed. Okay. The efficiency, how fast or how slow the algorithm is running, is expressed in terms of the number of elements that has to be processed. Basically, the number of inputs. Okay. Uh, so if n is the number of elements, then the efficiency can be stated as efficiency is equal to now, n is the number of elements, the inputs or the variables that are to be processed. So the efficiency will be f of n. Okay, f of n is also called the complexity. Efficiency and complexity are the same thing. So it will be represented as f of n. N is the number of elements. The second point is if a function is linear, that is without any loops or recursions, which means that the algorithm or the program does not contain any for loops and while loops, anything related to loops, okay, or recursive functions. It does not contain any loops or recursive function. It is called linear. So if a function is linear, the efficiency of that algorithm or the running time of that algorithm can be given as the number of instructions it contains, which means when there are no loops or recursions, we consider the number of instructions. What are the number of instructions inside that algorithm or inside that program? With the help of that, we define the efficiency or complexity of that algorithm with the help of number of instructions. Okay, the number of instructions will become n, and we have fn, which is the efficiency or complexity. Now, if an algorithm contains certain loops or recursive functions, then its efficiency may vary on the number, depending on the number of loops and the running time of each loop in the algorithm. Here are two important points. Okay, the number of loops and the running time of each loop in the algorithm. For example, we take two programs. Okay, or we take two algorithms. The first algorithm contains three loops. Okay, three for loops. The first algorithm contains the running time of each loop is 1 second. Okay, and in the second algorithm we have only one for loop. Okay, and the running time of that for loop is 5 seconds, right? So the running time of the first algorithm, which contains 3 for loops, will be 3 seconds in total, because each for loop takes 1 second to execute. And in the second case, in the second algorithm, it takes 5 seconds to execute a single for loop. Now, which algorithm or which program will be more efficient? The first one, even though the first algorithm has 3 loops, the combined total time required to run that algorithm is 3 seconds, but the time required to execute or run the second algorithm is higher, which is 5 seconds, right? So the first algorithm will become more efficient despite having the larger number of loops, right? So the efficiency or complexity depends on both the number of loops and the running time of each loop. Okay, we move to the next slide. This is a nice example of big O notation. Okay, so this O is called the big O, and this is called the big O notation. Okay, this represents the complexity. Now, this graph here represents how the time required changes with respect to input size in different orders. Okay, this is the order of n square, this is read as the order of n square, this is read as order of n, this is a linear function, this is called order of log n, this is a logarithmic function, and this is order of 1, which is a constant function. Okay, with respect to input size, the time does not change, so this is a constant function. You can easily see that for a slight increase in input size, the time required in case of order of n square, the time required increases drastically, which is not the case with logarithmic function, which means the logarithmic function has less amount of required time, which means the logarithmic function is more efficient than the n square function. Okay, for this area after this point, okay, after this point, the logarithmic function is more efficient than the n square function. Okay. Similarly, we have this representation of best to worst, the best to worst efficiency or complexity of different orders. The first one is constant, which is the best order, order of 1, and the last one is factorial, which is order of n factorial. N factorial, as we know, n factorial represents n into n minus 1 into n minus 2, so on to 1. Okay. So this order represents which is the best, which means which is the best algorithm regarding efficiency, and which is the worst regarding that efficiency or complexity, as we can say. Now, I told you the n square order is worse than the log n. Here we can see logarithmic is one of the best orders, and quadratic is worse than logarithmic. Cubic is even worse than quadratic, polynomial is even worse than cubic. Similarly, factorial becomes the worst since the value and factorial will be much higher. Okay. Now we move to the next slide. Now we talk about loops. Okay, how different loops have different orders. We'll talk about three types of loops. First one is the linear loops. Here we have a for loop which contains the counter I. I is moved from 0 to n, which is n minus 1, I less than n. We are running this loop and we are increasing I 1 by 1 every single loop. Okay. So the linear loop will have the order of fn is equal to n, or the order of n, because this loop is running n times. Okay, this I, the counter I, moves from 0 to n minus 1 and increases by 1 every time. So this will run for n times, and hence the order of this linear loop will be order of n. Okay. Now the second kind of loop is logarithmic loops. Logarithmic loops are something like this: I is equal to 1, I less than 1000. I is moving from 1 to less than 1000, which means up to 999 some point something. Okay. And I is increased by multiplying by every uh, recursion cycle. Okay. So after the first recursion cycle, I is equal to 1 is multiplied by 2. This represents I is equal to I into 2. Okay, I multiplied by 2. So 1 is multiplied by 2, I becomes 2. After another loop, I which is 2 now, again multiplied by 2, which becomes 4, I becomes 4. So similarly, I will continue until it is less than 1000. Okay. If it exceeds 1000, this loop will not be executed. So since I is increasing 2 times every time, okay, this can be represented as 2 to the power of something, okay, right? Because 2 to the power of 9, which is 512, is less than 1000, and 2 to the power of 10, which is 1024, is greater than 1000. Okay, so the loop will be executed 9 times, okay, which iterates 9 times. Similarly, in this case also, I is decreasing from 1000 to 1. This statement means I is equal to I divided by 2. Okay, so this will also execute 9 times. It is similar to this. This is increasing and this is decreasing the value of I. Both of them will iterate 9 times. So in both of the cases, the order will be in the log of n, right? Log 2, 2 is the base and 1000 is the exponent. 2 to the power of 9.96 is equal to 1000. Okay, so we take the log on both sides with respect to base 2. Okay, so we get log 2000 is equal to 9.96, which is across 9 times. Here we saw the iteration of 9 times, right? So fn is equal to log n. Okay, or order of log n. This is the logarithmic loop, right? Now we move on to nested loops. The first one is linear logarithmic. Linear logarithmic basically means a logarithmic loop inside a linear loop. Okay, so here it is a linear loop. I is equal to 0, I less than n, which means it will run from 0 to 9, and I plus plus. And inside that for loop there is another for loop. The counter is j this time, which moves from 1 to 1000, similar to this I 1 to 1000, and j is equal to j multiplied by 2. This statement block is executed every cycle. Now these are linear and logarithmic loops, one contained inside another. Okay. So this will be giving us the function of n is equal to n log n. We have multiplied n by log n. The first case had order of n is equal to n, and the second case has order of log n here, and that is why, because logarithmic loop is inside the linear loop, we multiplied both numbers and got the order of n log n for this whole algorithm or this whole loop, right? Now similar to this, we have another case which has a for loop inside another for loop, and both are linear. Okay, where I is equal to 0 to n I plus plus. For 0, j is equal to 0 to j less than n, j plus plus. Here it is not multiplying or dividing like this. Both of them are linear, like this first case. Okay, so we multiplied n by n. Right, here we multiplied n by log n. Here we multiplied n by n because this is n are the order for each loop. And since one loop is inside another loop, we have to multiply the order of first one with the order of second one, and we get n square, which we can also say it is the order of n square. Now, I hope you understood all of that, and In the next lecture, we'll talk about the time complexity of matrix addition and multiplication and also some other stuff too. Till then, take care. Bye bye.